The purpose of the strain-calculated apparatus for load evaluation, scale, is to provide a cheaper alternative for commercially available sitting scales and wheelchair scales, which are used by people with mobility impairments. The prototype is a steel frame stool with a wooden seat supported by 4 beams, each with a strain gauge measuring its bending. The calibration process involved recording the voltage output of the system for several known masses and creating a linear fit to that data. The linear fit is then used to calculate the weight of an individual based on the voltage output of the system. This concept uses simpler manufacturing and cheaper electronics than previously existing products. According to the CDC, 12.2% of U.S. adults have a mobility disability. These individuals may not be able to stand on a regular scale. For this reason, scales that are chairs and large scales that wheelchairs can roll onto exist. However, these specialized equipment are extremely expensive, costing thousands of dollars. This creates a cost barrier, which results in less than 15% of primary care practices having accessible weight scales, and very few individuals being able to have them in their home. Our prototype is for a new design that can find use in primary care clinics as well as individual home use. Instead of using specialized load cells supporting the platform that a seat is mounted to, our concept is to mount a standard strain gauges to the structure of the seat itself. In use, a mobility impaired individual will shift from a wheelchair or scooter onto the sitting scale chair. This may require the assistance of another person in some cases, but will be similar to getting in and out of a regular wheelchair. To ensure that the system is as accurate as a standard bathroom scale, an accuracy of plus or minus 0.5 pounds at 95% confidence is required. This accuracy must be true within a range of 90 to 300 pounds. To ensure a wide safety margin, the CAD model was simulated under 600 pounds without failure.
The chosen design for the scale includes a full bridge sensor that could easily be read with the National Instruments MyDAC that was readily available in the lab. Additional considerations for the design of the scale include the length of the cross brace and the material cross section. Preliminary calculations were performed to determine the ideal sizing for a range of loads that would be experienced by the scale. The overall design of the scale was chosen to be tall and symmetric to simplify loading conditions. Some alternative designs for the instrumentation of the scale considered but not implemented were reading the strain gauges individually as quarter bridge sensors with complementary resistors to complete the bridge, not using the Takuna Systems amplifier and instead reading the voltage changes across the bridge with the DAC. Additionally considered were reading the strain gauges individually with the Takuna Systems amplifier for each strain gauge, and different placements of the gauges were considered on the vertical legs and above and below or in the cross brace of the beam.
To simplify the theoretical model, certain assumptions were made. The calculation in the analysis assumed that all beams share equal loading and that the load is applied perfectly vertically. We assumed that the load induced pure bending and there's no torsion of the beams. The material properties assume that the metal is 1020 cold drawn steel in linear elastic deformation only. In this experiment, there are several key variables to allow us to compare our results to the theoretical model. Some of the variables used in our uncertainty calculations are the modulus of elasticity of our building material, the distance from the applied load to the strain gauge, the output voltage, the amplification factor of the Takuna amplifier, the excitation voltage, the gauge factor of our strain gauge, and the thickness and side length of our square hollow beam metal used to construct the chair. The associated uncertainties for these variables are found from the manufacturer specifications, online databases, and from measurements taken using the most precise instruments available. The strain on the scale prototype was measured using National Instruments MyDAC. To gather calibration data, we weighed an individual or object on a standard bathroom scale to obtain a known weight value, which was recorded into an Excel spreadsheet. After the weight is recorded, the individual or object was placed on the seat of the prototype, and the voltage output was measured for 5 seconds. The average voltage was extracted and recorded in the spreadsheet for analysis.
The collected data was plotted, resulting in a linear relationship. We used Excel to generate a trend line, which had a low R-squared value of 0.9805. The equation generated is used as a mathematical correlation between raw voltage and weight of an individual. In order to theoretically determine the weight of the user seated on the scale, the team can use the stress-strain relationship using Young's modulus by calculating the strain experienced on the beam using our strain gauges. The material properties of the metal in the scale allow us to find the stress in the beam. The following equations were used to create the theoretical model for determining the weight of a person seated on our scale. Once our governing equation was derived, this allowed us to determine the overall theoretical uncertainty of our measurements of a person's weight while seated on the scale.
Below are the measured or given values used to theoretically determine the user's weight. To simplify, the error propagation, the thickness and side length of the hollow square beam used in the beam stress calculations was algebraically grouped into a single geometric factor, A. This substitution extracts fourth-order partial derivatives for beam width and wall thickness into a single uncertainty value used in the final theoretical uncertainty equation. The thickness and side length of the beam were measured using micrometers to minimize the effect of that uncertainty on the total uncertainty of the calculated weight. Error propagation was performed using the below equation based on our governing equation. Using the Klein-McClintock method, this equation was generated taking into account all variables that have an associated uncertainty in the theoretical calculation for user weight. Variables included in the error propagation equation were Young's modulus, distance from strain gauge to applied load, output voltage, amplification factor, excitation voltage, gauge factor, thickness of the beam, and side length of the beam. The thickness of the beam and side length of the beam were simplified into a single geometry factor as explained. Our total theoretical uncertainty was found to be 3.87%.
When we calibrated using all 54 measurements, we did so across 3 distinct conditions. First, we took an initial set of readings. This is our baseline. Then, after a 2-hour gap, we repeated the calibration to capture any drift the scale might experience over time. That's our second condition. Finally, we physically reoriented the scale and took a third set of readings to test how sensitive the calibration was to the scale's position. When you combine all 3 conditions, you get a reduced chi-squared value of 2.21, meaning our residuals were about 1.5 times larger than the error propagation formula alone predicted. That excess is primarily explained by those 2 variables, the between-session drift and the orientation sensitivity, things the formula didn't capture. The expanded uncertainty at 95% confidence is 14.3 pounds, which is load dependent. At 50 pounds, it's nearly 29%, while at the top of our range, it drops to 6%. 94% of measurements still fell within that bound. When we isolated just the first of the 3 data sets, same orientation, same setup, the picture improves significantly. The reduced chi-squared drops to 0.83, which is essentially 1, meaning the calibration residuals are fully consistent with what error propagation predicted. The expanded uncertainty is plus or minus 7.75 pounds, half of the full trial result. More importantly, at the loads this scale is actually designed for, 90 pounds to our max tested value of 230 pounds, that works out to between 3.4 and 5.2%, which is closer to our theoretical 3.93%.
The calculated theoretical uncertainty of plus or minus 3.87% was lower than the calibrated uncertainties that were the highest at the lowest weights. The biggest calibrated uncertainty factor was due to voltage drift in our output voltage reading, which we attempted to limit using several different methods, but ultimately went unresolved. Throughout calibration, our outputs consistently gave linear results, but when measured at different times, the starting zeroed out output voltage would slightly drift, requiring tearing. Other factors affecting the calibrated uncertainty could be due to inconsistencies in welding and assembling a stool, as well as inconsistencies in installing strain gauges, which result in different loads or different readings of loads in the beam, which were assumed to be equal in the theoretical model. During our original calibration, before this drift was present in the data, the calibrated uncertainty of 3.4% was achieved at 230 pounds. Overall, the calculated uncertainties were greater than our original desired uncertainty of plus or minus 0.5 pounds. However, we did demonstrate that this low-cost system is feasible for the purpose with certain improvements. Certain analysis methods from class were not used. Students' t-distribution was not used because our data set was sufficiently large. We did not use a central limit theorem since we are not trying to establish a normal distribution. We did not use sample statistics because we used the full population of known weights. For the frame, the 14-gauge square tube was selected because it is stronger than the 16-gauge and easier for manufacturing than the circular tube. The 120 ohm pre-soldered strain gauges were selected because they are more precise than 350 ohm gauges and do not require difficult soldering. The amplification and bridge setup that was selected was the Takuna Systems amplifier with an internal full bridge. This simplifies wiring and setup and amplifies the output for more precise measurement.